Hello, this is Pascal from Florida, and in this video, I'd like to quickly go over a causal inference notebook that I wrote last summer. The example in this notebook is based on the slippery sidewalk example in the Judy Pearl causal inference primer book. Um, and let's start with this causal graph here, where x1 represents whether a day is sunny or not, x2 represents whether the sprinklers are on or off. X3 represents whether it's raining or not on that day. Then X4 would be if the sidewalk is wet or not, and X5 is if the sidewalk is slippery or not. And so, for example, if X1 was 1, that is that it is a sunny day, you would expect that the sprinklers would also be on, and that it wasn't raining, or it's less probable that it's raining. Versus if x1 was 0, then it's less likely that the sprinklers are on because it's not a sunny day, and it's more likely that it's raining. Then x3 would be 1. All right, so let's move on to the counterfactual now. So shortly, a counterfactual is taking a graph like this and doing an intervention on it, but not at the level of the population, rather at the level of an individual. So I'm not looking at the probability of x4 being 1 or 0 if I intervene and set the value of x2. No, I'm looking at a very specific instance, something that's already happened. And I want to go back and, given all that's happened, uh, uh, intervene and see on that very specific instance, do I get a different result or not? And that's the question that I want to answer. But so in order to do that, I'm going to describe my variables here with these equations. And so everything, and I'm assuming a linear relationship between them. And so everything to the right hand side over here is a cause for the left hand side, right? So, and the u's would be the exogenous causes. And those are things that I cannot account for, but that are still causes for this variable. So, for instance, maybe the sidewalk is wet because somebody, spilled water or something that I cannot account for, and I'm just going to use u as something, as a variable to hold all these things that I cannot account for. And so then I'll fit a model for x4, x3, and x2, and from this model I'm going to get the intercepts, which is going to be the exogenous variables, and then the coefficients for each one of those expressions. And now I've set the situation, right? I've set the scene. I'm going to let the experiment run. So let's start by saying that x1 is not a sunny day. And I'm going to let the experiment run. And I get that the sprinklers are on, which is not necessarily what I would expect, but they're on. And the sidewalk is wet. Okay. So now what I'm going to do is I'm going to go in and set x2 to 0. That is, I'm going to go in and shut off the sprinklers. See, what I'm doing here is I'm just letting the experiment run. X2 takes its value from the model. But if I go in and deseparate x2 from x1, given that the experiment already ran and I know all these factors, what happens then? It's almost like going back in time. And so this expression here reads, what would x4 be had x2 been lowercase x2, had x2 taken on particular value. Um, and so now x2 is 0, right? It's no longer model x2 predict yada yada yada. It's no longer a cause of x1 and a cause of the graph. It's deseparated and has its a value that I set. And now I'm going to let the experiment run again and observe that the sprinkler are off, obviously, but that the sidewalk is still on. Right? So the sidewalk wasn't on necessarily because the sprinklers were on. It's very likely that because it was a sunny day, then maybe it was raining, and that's why the sidewalk were wet, right? And so this is a trivial example, but you can already see its usefulness in that I can pinpoint, the cause of an event. And also it's useful because it saves me a trip outside if I know that it's not going to help anyways, right? To shut off the sprinklers. All right, thank you guys.